everybody. Back to the ICT Kent seminar. My name is Ramis Haj, and I'm an assistant professor here at UIUC working with ICT. And we're really excited about this year's Kent seminar series. The focus will be on transportation and climate change and basically sustainable approaches to transportation. So thank you all for joining. If you're in the class, you will also get more information from Professor Okadi about what you need to submit if you're registered for 1 credit hour. But for now, I'm going to go ahead and introduce our first speaker of the semester. We're really honored to have Professor Jeffery Roesler, who is a professor here at the University of Illinois. Dr. Jeffery Roesler holds the Ernest Berenberg Professorship in the Department of Civil and Environmental Engineering at UIUC. He holds all of his degrees, his bachelor's, master's, and PhD from the Department of Civil Engineering at the University of Illinois Urbana-Champaign. And he's been conducting research on a variety of rigid pavement topics for the last 25 years. His recent interests are microscale urban heat island and cool surfaces, passive material sensing for vehicle lateral positioning, which is what he'll be talking about today, and non-contact ultrasonic sensing for construction monitoring. He's authored and co-authored more than 250 publications, and he's a registered professional engineer in California and an active participant in TRB, ACI, and is the past president of the International Society of Concrete Pavements. So with that, I will go ahead and welcome Professor Roesler.
All right, hear me all right in the back? Perfect. Thank you, everyone, for inviting me. And even invited me in the first one of the semester. So, and I'm excited to talk about this topic just because we've talked very little about it. Maybe if you know the student who worked on this, you heard about it, but if you didn't, then you probably didn't hear much about it because we're developing some things that we're pretty excited about. So I'll get right into it. I will warn you, there'll be a little quiz as part of this. It'll be an upfront quiz, so but no grading quiz. So Sachindra Dahal was a student on this project. He currently works at Electric Power Research Institute, looking at electric vehicle infrastructure. And this really all the funding that went into helping develop this idea into reality came from the Center for Connected and Automated Transportation as part of the Center at Michigan. That has been ongoing. I think it ends at the end of September, and actually it just got renewed again. So we're excited to continue work in the general space of automated transportation. So we appreciate the support from the University Transportation Center program. And I'll just disclose that we're currently in the final part of submitting the final patent application. We've already had a provisional on this work. Not everything I show you is actually in this presentation for a variety of reasons, but at least the general idea is in here. And Sachindra, with his help, we started a company based on this provisional patent that is looking to commercialize. So starting the company is somewhat easy, but actually doing something useful and getting it out there is the hard part. So it's still some work to start a company now that we've experienced it with this, but I think it's a good exercise when you develop something to see where it can go. A little story, since this seminar is somewhat related to a student group here and in Zoom, is I don't know why I didn't think more clearly earlier in my career about entrepreneurial mindset, but I want to at least show somewhat of how this worked out for this project, where I was asked to teach a class that no one wanted to teach, which is geometric design. And I had a good attitude about, okay, I'm going to do it well. That's part. So Sachindra, actually, I asked to be my TA in that class. So that's one part of maybe you think that has nothing to do with what you're currently doing. And that's kind of how I thought about it. Secondly, we then had a project with a tollway where we had to install sensors on a highway, and we used some wireless communication and then uploading to the cloud. So we never had to visit the site. And we had a lot of sensors. So we didn't want to we wanted to eliminate wires as much as possible. That was the idea. And so Sachindra led that effort with very little sensor background. And some of the students here actually helped with that. So they remember that. And then lastly, we had this opportunity to look at automated transportation. And the previous experiences kind of helped get the ball rolling about, okay, we've identified potentially a problem and now we can look into it. So the kind of the summary here is that being curious about a slightly different fields, about how it's working within things you know, and looking for opportunities or creating value in that field where you can apply something that maybe you just find as a niche that no one else has really thought about or not looked too much into. And so whatever you're doing, don't try to make connections between things you're doing, even if you think it's not worth your time, because you may be able to think about a problem slightly differently than the way people are thinking about it in that area. Okay, so here's the quiz. I'll give you a couple seconds to read these. I think it's important because I want to at least part of this talk is actually talking about some of these facts here. So some of these are facts and observations that are needed a little bit later in the talk. So you know, I'll summarize them here quickly. You know, do you know how many people died last year in the U.S. due to traffic fatalities?
36,000.
That's wrong, but that's close. That was so you're at least in the right ballpark. Yeah, but most people don't get that even right.
36,000.
Secondly, we'll get to the answers in a second. Secondly, what's the primary driving maneuver that leads to fatalities? So there is an accident that killed somebody. There's many reasons for an accident, but what's the primary driving maneuver that happens right before the accident? And then, yeah, and like left turn would be an answer. That's not the right answer, but and then the question is, well, what percentage of those maneuvers are of the total? So there's different actions. So left turn would be one, and maybe it's 10%, right? Left turn, then you get hit, T-boned because you turn in front of somebody. So that may be like 10%. I don't know the exact number. The next one is the difference between ADAS, Advanced Driver Assist Systems, and automated vehicles, autonomous vehicles. You know, what is the difference there? And I want to point that out because it's an important part here. Everybody's talking about autonomous vehicles. I will say that we should be talking more about advanced driver assist right now, more than autonomous vehicles. And I'm not against autonomous vehicles. I'm just saying there's some opportunities right now that connects the first two and really makes an impact. And then finally, anything we do, if you think about advanced driver assist systems, you know, you think about the whole road network. So how many lane miles of road just in the US? So if you think about applying something, you know, what's the scale you have to apply something?
88 million.
88 million?
8.6 million miles.
Yeah, I mean, that's pretty close. Yeah, 8.6 centerline miles. Anybody want to take a final guess at the driving maneuver here?
The lane miss.
Lane assist?
Well, like you miss the lane and you have that lane change.
Lane departure.
Lane
Yeah,
departure.
yeah, that's the number one driving maneuver. And anybody want to take a guess on the difference between these two, ADAS and AVs?
Need a driver for ADAS.
Yeah, I mean, that partially correct, but probably not. Yeah, it's halfway there maybe. I mean, you think about ADAS being kind of the overall advanced driver assist systems, and an autonomous vehicle is a special system where you don't need the driver to work. So ADAS, current vehicles you buy, a lot of them already have advanced driver assist, right? Blindside monitoring and automated braking. These are ADAS systems. You still can have a driver. If you want to move to autonomous vehicles, is separate. You know, you need to have a bunch of other things happening at the same time. And the final one, the traffic fatalities. There you go, almost 43,000 deaths per year. Okay. And the other one is that's shocking here is 42% is in rural, so non-urban. It's just not that there's a lot of people around. People are doing lane departures even in rural areas by themselves. There's a big program with FHWA called Vision Zero.
I thought we were down to 30,000, that's,
Yeah, it went down and it came back up. Yeah, we're up. I'll show that statistic in a second, but it went down. So the funny part is, I'll hit on this right now. Ever since we've had advanced driver assist systems, actually everything's gone up, more or less. And I'm not sure it's because of those things, but what's that tell you about driving behavior, though?
distracted, and like cell phone and.
Yeah, there's other factors coming in there. Distraction, a big factor. How much of that plays in their role? Probably a pretty large percentage of it. Speed is higher now. You know, speeds are higher. So yeah, despite technology, despite FHWA's great vision here, and I don't have a problem with it, traffic deaths actually have gone up, and they spent a lot of money trying to improve geometrics, improve shoulders, rumble strips, roadside features, and yet we see fatalities moving upward, not downward. We've already talked about that, and this is my definition. It's a subset of ADAS, and this is since 2011, we were down at 32,000, so things have just gone up, and we're about 20% from 2019. And someone already got the 8.8 lane miles. So this is another way to look at. You've probably seen this before. Level 2 is a lot of cars you can buy now. We have a Subaru, which isn't a really expensive car, but you can pretty much get level 2 features on that. So blind spot monitoring, adaptive cruise control, automated braking, object detection and braking. I mean, those are all really nice. And then lane keeping, you know, with lane keeping is also in there. So these are what I would call ADAS systems, and there's more out there. And then if you back up, you have the rear view camera, front facing camera, and then you have cross traffic as well. So I've kind of talked about these already. I'm not going to go into it again. And of course, autonomous vehicles get all the news, and they use all these sensors in a way that they can be confident that the driver doesn't have to touch basically the steering wheel. And there's all these benefits that people are talking about. But I'm not, again, the talk's mostly about this is nice, but maybe this isn't the next step. We need to have an intermediate step potentially to make this work even better, particularly with the traffic fatalities at 43,000. We're not really making a dent. And I would say that our current strategies to make dents are not very good. I mean, if we talk about a 10% drop in fatalities, we don't even get back to 2019 levels. So how are we going to get there? What are we going to do as transportation engineers to get there more rapidly? That's the question I have. And no, lane departures causes 50% of fatalities. Now that could be a drunk driver, right, that leaves their lane. So that's complicated, but at least leaving the lane initiates a death. So we have all kinds of sensors on the cars that we're going to continue to use for safety. And the question is, are we really moving rapidly to use those to keep the passenger and pedestrian safety? So I'll talk a little bit about AVs just because it fits in nicely. We can navigate with automated vehicles, even with non-automated vehicles, you can navigate pretty well. Obviously you can't steer by yourself or with the vehicle. But one of the ones I want to spend some time on, most of your lane keeping algorithms, or all of your lane keeping algorithms, as far as I know, basically use a camera that's stuck up by your rear view mirror. It looks forward, it detects the lines on the road, and whoops, it didn't show up there. And then it tries to keep you in between the detected lines here. So obviously, if you don't have lines there or some side of contrast, you may have a problem, right? And that's one of the things that came out of our geometric design class. So we had students in the class, like, what would you do to design a autonomous vehicle road? And you start thinking, everybody's saying You know, there's not, the road is neutral. You don't need to do anything. In reality, you do. You need to have good lane markings, very good lane markings, because that's how these work. If you don't have lane markings, you're in trouble. Okay, so what's the problem then? Well, we could have lane markings, but I'll go back again and let you look, but we'd have to maintain lane markings at a very high level. And remember, 8.8 million miles, right? That's a fair amount of maintenance. Probably good for the lane marking people. But even if you have snow plows, it can rip off lane markings. They fade. We were driving up here with Professor Ouyang on 45, and if you're looking ahead, the lane markings disappear. The asphalt kind of gets very light, and the lane markings are light, and you can almost not tell with your own eyes the lane markings are there. So even if they're there, the contrast is not maybe good enough. Now we haven't talked about bad weather. So if we have adverse weather conditions, you have a very hard time detecting where you're at, the car automatically. So you see a lot of the tests that are done are in Arizona, California, where you have nice sunny days, no adverse weather, very little rain, no fog, no sleet. And that's fine. I mean, that's nice. But this is a serious challenge if you think about the Midwest, where 33 states get 10 inches or more of snow. Okay. The interesting part, again, if you read the National Highway Safety Administration report, 75% of fatal crashes actually happen because of lane departures in adverse weather conditions. So you're kind of hoping for advanced vehicles to help you, but they're going to have problems in adverse weather conditions. Okay, so yes, there are people trying to work with the computer technology to kind of get around how they can figure out how to keep the lane and not deal with the road. Okay, so there's people working on that. If they can fix it, that's great. I'm a little skeptical that they will, because if you can't see it with your eye, it's going to be hard for a camera to see it as well. But they're trying it for LiDAR, they're trying it for camera-based systems, and nothing's come up with that yet. There's obviously other things to do. You can build a roadside network that you can talk to your vehicle with. Maybe that'll be useful in the future for many reasons, maybe in urban areas. But in the short run, this is probably not a solution either, and it's probably too expensive. Given the amount of lane miles of road, you're not going to have roadside units for 8.8 million miles. In urban areas, I could see this happening. So these are the challenges. So I'm kind of setting up the problem here. It's taken a while that we kind of came to eventually. So this took about 5 years. So I'm crunching this down to about 10 minutes. Where there was a problem that the vehicle, I think people say, well, we can do 80% maybe, or whatever the percentage is. We can get it right, 80, 85, 90%. Well, that's really not good enough if you're driving, right? Every 10 miles, you know, we have one of those miles where your vehicle doesn't know where it's at. It's probably not good enough. So we need something that's weather independent, and so passive sensing came into play. Suchendra and I talked about this, and of course, the first thing people talk about is RFID tags and planting those in the road, and we kind of dismissed those pretty quickly because the depth, sometimes you need those, plus you still need to maintain them, plus you need to embed them initially. So you start talking about this, and it seems like, well, it's probably not going to ever sell. It could work, but it may not be something that's efficient and easily maintained. Especially when you talk about where all the roads are. And so really interstates would be easy since you're only 5% of the network. But when you talk about most of the, let's say the delivery system and people moving around are in these arterial to collector, minor collector area, they're not in the, this is not VMT, but percentage of the lane miles. So we also looked at other ideas. I'll tell you what we dismissed. So we thought, well, maybe there's optical ways where we could look at certain areas of the road, we could change the optical properties or the way it emits radiation. And that could go with the thermal properties as well. If we change slices of the road, we may be able to detect them with IR cameras to some degree and be able to navigate that way. And we kind of dismissed all those because of just the complicated sensing that would need to be done, and adverse weather conditions would still be an issue. People have looked at radar. People are still looking at radar as a way of embedding something that you can kind of shoot off in the forward-looking direction. And I'm not saying this would never work, but you still have a lot of reflectors to some degree around the road. So you're going to have to deal with other vehicles, guardrails, signage that reflect signals that you're not going to be able to detect and put yourself accurately in the lane. Finally, we're stuck on a fairly simple idea, which is conductance. So if we can have a conductor on the slice of the road, and then we can detect that. We can just find our lateral position. And in this case, we can do it with an air gap. So imagine you do if you've ever done metal detectors, right, on a beach looking for jewelry in the sand, you do that basically in the water or on the sand, and you can have an air gap, and it'll make a noise and say there's some metal down there. It's the same idea here. So we said, let's try this. So basically, you would create, put some kind of conducting material, and that material, however we want to embed it, we can embed it in concrete or asphalt. Can do it new or rehab. We had to have something that works for all the different cases, and then have a fairly cheap sensor. That's the other part. We can't have a $20,000 sensor, so a eddy current a loop sensor would be pretty cheap to make, and we did that. And so the idea then is you kind of put some sort of conductor in the longitudinal lane somewhere. It could be in the center, it doesn't have to be. And your vehicle could use the camera-based system until maybe you had some occlusion where you don't see the lane lines anymore. And then this backup system comes online, and you can detect generally where you are until the camera system works again. So this is the idea that we come up. And essentially in the space, you have this invisible signature that you've created, right? You have this conductor that when you excite this material with a magnetic field, you can then detect that there's something there, and you know the position of that. So this was our initial take on it. Essentially, yeah, we have a high conductivity material. So something like steel, anything with steel is going to conduct well. Could be other things, but that's a simple example. And generally, materials that we use, asphalt and concrete, are low conductors. So we just have to replace a small sliver of that in order to figure out where we are in the lane. And I'll tell you up front that we ended up not using this, but I'll just show you in principle why it's important, because then we switch to something else here. But this is basically how the eddy current works, where you have a coil with wire that's in a circle here, and this would be the pavement where you have some metal like fibers, and this magnetic field gets created by the coil and creates a current here, which then puts a secondary magnetic field up here, and you can detect it. So that's how basically a metal detector works as well. And of course, the bigger the diameter, you can detect deeper, and the closer you are, the better you detect things. But there's some trade-offs here. If you want to do better, you have to make it bigger, but then you detect everything, and that's not good either. So there's challenges with this from the start. And but we came up with this sample. So this could be concrete or asphalt. We did concrete. And what we found was we wanted to look at different materials that we could notch in there. So we cast two separate samples, and the prism samples we just stuck in there so we could make different materials. So we didn't have to use just steel. We could use other types of conductors, and we could vary the volume of material we use. Because ideally, if we have to do 8 million miles of this, we'd prefer it as something as small as possible, right? That we could, let's say, saw cut in, put the material in, and they would just be there. So that was the idea with the notching, that if I had roads already in existence, we could just mill out a little 1-inch chunk, 1 inch deep, put this material in, and move on. And so we looked at different electromagnetic material that we could get signatures. And so here's our laboratory. This is our very homemade eddy current device that Sachendra made. And we had a robotic arm that could go back and forth like you were driving your car, right? This would be like on the front bumper, and you could imagine it going back and forth to kind of simulate. And then we looked at, oh, what happens if you have snow on the surface? That's what you see here. This is generally how it works. And you can see this would be snow, ice. We had debris on there just to show how it worked. And we could then have different heights of materials. We could have different volume fractions of materials in the road. And so here's what we ended up finding. So the green there is basically the conductor material like steel fibers. And we could put different dosages in there, for example. And so this is generally what it would look like. So your signals, even with relatively low dosages, 0.5% by volume, which is pretty much what you would normally see in concrete if you use steel fibers, you can still detect in the middle where the position of the vehicle is. Obviously, steel fibers wouldn't work very well for asphalt, so I'm not, I'll say that up front, that I wasn't proposing steel fibers for asphalt. But obviously, if you could get a conductor to work, you could obviously embed that in a narrow band, assuming it conducts enough. We looked at a bunch of things just to get an idea of what are some of the most important factors, and obviously the height above. So, you know, with eddy current, you need to be pretty close. The higher you get, the signal kind of deteriorates. So that's an issue. That'll be an issue with anything. You need to have it high enough, maybe let's say 1 foot to 18 inches above the road. But obviously, with the eddy current system, ice and water doesn't really get affected by it, which is good news. That's really what we want. We kind of knew that already. We knew that already, but we just wanted to demonstrate it. Obviously, the smaller the prism, you have a trade-off with how small you go with what the volume fraction you're putting in there, and then how conductive is the material. So there's a bunch of variables in there. How much does it conduct? How big the particles are, because it has to develop an eddy current in it. So this in itself doesn't tell you the whole story. But generally, the whole concept seemed to make sense. So if we get something to work similar to this, it seemed like it would be a relatively good idea, at least to kind of complement that other system. So obviously, cars have a lot of conductive materials. They're not all made out of plastic. And this has become a major problem. Like, no matter what we did, we could research this for another 5 years. We would really have a hard time overcoming the problems of other vehicles, other metal on the highway, to the point where we couldn't deal with this. So we just kind of decided to abandon this, mostly because Sachendra came up with another good idea, which is what you expect your students, like, come up with, like, the problem's still there. We need a better idea. That's what we need. We don't need, the problem's not disappearing. And we looked in, I was a postdoc at Berkeley in 1998, and I recalled some weird stuff going on there I wasn't completely familiar with. I knew they were trying to do automated vehicles back then, and they were drilling holes into the road, and I always thought that was a bad idea. So I went back and looked. I remembered I went back and looked what they did. And what they ended up doing is they drilled holes. This is a top view here. Drilled holes every 4 feet, and they put permanent magnets in the road. And that was the way they were going to track where vehicles were. And they had certain signatures on the magnet to tell you where you were. So had a very nifty idea. Like, it was a great idea. Maybe the implementation and the sensors they were using weren't quite ready for what we needed, but it was a good idea. And eventually this got abandoned for several reasons, but essentially with permanent magnets, you can create this signature you can pick up with a magnetometer, a magnetic sensing device. And you could also create different signatures to tell you something, like depending on how you created the permanent magnet, it could tell you to say, oh, there's an exit here, or there's an intersection coming up here, so the vehicle would know where it's at. One thing they found was, I mean, the big thing here is, imagine you're drilling, you know this because most of you are pavement engineers in the room, drilling holes, epoxying things in. This could be problematic, right? They're going to come out, magnets are going to break. So these are permanent magnets. So they had a lot of issues with just maintenance. And if you think about 8.8 million miles, that becomes, you don't have the capacity that you need something very reliable, permanent. The other thing is, one thing they didn't do, as far as I can tell, is these magnetic sensors, they monitor the general magnetic. So if I have a magnetometer with me, which I didn't bring, I could monitor the magnetic field right here. Well, it includes the Earth's magnetic field, as well as anything else around here. Any metal around here it'll pick up. So you have to kind of pre-map the roadway to determine the kind of the signature of the roadway so the vehicle knows what to expect. The problem is if things change in the roadway, like you put a guardrail in or the Earth's magnetic field does actually change a little bit, then all of a sudden this becomes problematic. It's not a reliable signal. So that was another downside. They probably could have got around this, which I'll show in a second. But so we decided, okay, let's head this direction with magnetic properties. We'll do the same thing. We'll try to get materials with high magnetic permeability. Okay, materials that really change the magnetic field locally, whether it's a permanent magnet or just a material that bends the Earth's magnetic field, which is what we actually ended up doing. So high magnetic permeability materials, they'll bend the Earth's magnetic field a lot, and then you can detect that at a much stronger signal. So steel fibers will bend the Earth's magnetic field, and you can pick that up relative to the background magnetic field that is out there already. So we did the same thing again. We just used slightly different ideas, a different sensor, and a different sensor setup. We called this, we use magnetometers, and these are 3D printed cartridges, the magnetometers inside of these. And essentially then, these detect this magnetic field flux change. So if you had no fibers, and let's say no fibers on the road, you would just basically be picking up either something with a magnetic property in the road, or you just pick up the background magnetic field of the Earth. When you put these two together and you subtract them, you get this gradiometer effect. So this subtracts out of the background noise, so then you get rid of the background noise. So that's the little trick that gets rid of the background noise. Pretty simple. And so now we can just we subtract out the Earth's magnetic field, and all we're looking for is local changes to the magnetic field intensity. Okay, so now we get, so even in our lab we'll pick up the Earth's magnetic field with one of these sensors, but if we subtract these two, it's gone, and we're just looking at local variations. So that was a big. It seems rather trivial since I'm explaining it, but if we didn't do this, it would have never happened. And so the other thing was, well, what types of materials have high magnetic permeability? And steel, and certain types of steel do, even steel fibers, but there's actually other types of materials that we found. Some of these are shown here. Met glass is a manufacturing material that has high magnetic permeability, so that you need very little of it to affect the magnetic fields that you can measure. And so we looked at different materials that we thought we could embed in asphalt or concrete. That was really the goal here. We had a couple other powders there, iron oxide powders, and we also realized that the shape of the material, the particle shape, affects also how it affects the magnetic field. So very fine particles weren't as effective as ones that were somewhat like a ribbon, where you could get some of the magnetic field lines to pass through it. And then, of course, you have different sizes of the prisms. So basically did everything again that we did before. We looked at heights above, we looked at volume fractions, we looked at the effects. And again, the ice, snow, sand doesn't really affect the signal whatsoever, because you're measuring the impact. You're just trying to measure how the magnetic field of the Earth is changed by those prisms. So this material in between it doesn't really matter. At least this material doesn't matter. And here's a couple examples. As you can expect, even with pretty high sensor height. I think this was for half percent or 1% of fiber volume fraction. You still get a signal, 500 nanotesla. 500 nanotesla is the unit here. The Earth's magnetic field is about 50 microtesla. So the Earth's magnetic field will wash out the signal if you don't have this radiometer effect. Here's the effect of fiber dosages. You can see 0.5% is still a reasonable amount to put in concrete. You can easily detect that at 9 to 12 inches above it. And then the last one here is looking at the size of that material. So if you shrink this down into one fiber, then you're going to have a hard time detecting it. So you need some volume fraction, or you need to change the material. That's the other side. I can change a material that has much more higher magnetic permeability. And here's an example. So we used this met glass material that was used for some other material science application. And you can get the very small amounts of that, not 0.5%, but 0.12%. You get a very high signal with the right shape. Obviously, this material costs a little bit more than steel fibers, but the point here is that if you get the right material, right shape, right volume fraction, right total volume, you can actually get this to work at hopefully a very usable amount. And here's a few other materials. We got some powder material and iron filings, and so the kind of the findings here is that, okay, when you do this design, you need to have some sort of minimum signal. We came up with somewhere around 150, 200 nanotesla was some minimum signal you would need to detect from a vehicle, basically. So you need to have some specification, say, if I can't get this signal level, then I'm not going to be able to detect it when I'm going high speed. So yeah, I think basically our lab results kind of showed, okay, this seems to work. And so the next step was actually just to go outside and just kind of demo it with some simple, a simple cart. So we put the magnetometers, we reduced the number of magnetometers on the surface. We just wanted to show if I had a camera-based system versus the magnetometer, could we track it with pretty good accuracy? This really was just to verify what we already kind of knew. So I think Sachendra did this at a university parking lot where we just kind of push carted this on several different paths. And we either pushed straight ahead or we pushed kind of an offset to see if we could detect, we want to be able to detect we're 2 inches off pretty accurately, or if we just kind of meander, can we figure out our path pretty easily? And we did a lot of this, and this is just one example of this is you can see up front here, there's no, this green is the camera-based system trying to do edge detections. And you can tell from that previous one that when there's no lines, it can't tell you where it's at. And this one here, it's following the magnetic, we have a magnetic tape in the middle with the magnetometers. And I'll do it one more time. The magnetometers, it's showing where the card is, where this red line is. So I'll do it one more time here. So here, there's no lines, and the camera-based system gets confused as expected. Once you get to the lines, it actually does pretty good, although it gets confused by the magnetic tape. And the second one here, again, we're using the magnetometers to kind of track where the vehicle is. You can see that up here. The vehicle is meandering like a sine wave. And so we can control where it's at, or at least know where it's at. So when you think about implementing that in a lane departure warning, you can just figure out where the center of the vehicle is and then warn the driver they're either going to have to move back to the center or send a signal or something like that. The final part of this, part of his thesis was, with this all, how accurate will this is? And that's not really a trivial question, because you have to know where the vehicle is, even in adverse weather conditions. So I think in the back here, you have this apron. So we set up a bunch of these prisms that we knew would work. They had steel, various types of steel or met glass in them. They're 3-inch prisms. And it's not a hugely long test section, but it basically would allow us then, we bolted on this sensor array on, this is Sachendra's car. This got bolted onto the front, then we put on side cameras, a bumper camera and a front camera. And that way we could then track theoretically where the car was, have the sensors track where it is relative to those concrete prisms like they were embedded. So we assumed that this was just embedding these into the asphalt layer, that's actually concrete, in the concrete layer there. And here's an example of the side cameras are the ground truth. That's hard to see. I'll move that. So the ground truth are red, and we had the camera, the side cameras looking at that white line, and we had a way of knowing the distance between the camera and the white line to know what the ground truth was. Here's the magnetometers, which is telling you where the sensors are telling where the car is. And so you get the front camera, which essentially is the camera you would have in a AV, and then you have the magnetometers, which is a backup system. So then we did this for several different conditions. This is the easy condition where you have lines. The camera does a pretty good job because it can see the lines. So the magnetometer doesn't have a huge amount of advantages. So we did this. This was the hard part for his thesis because we had to wait till it snowed. Luckily, the first year it snowed, or he's been in here another year. This was in the last year, excuse me, so he would have had to extend it to the next year. So we had normal conditions where we ran a bunch of tests and got some data. Then we had one where it's not much snow, but actually a camera system has a very difficult time tracking where you are in this lane. So let's say you probably wouldn't send out a snow plow, but these camera-based systems wouldn't be able to do lane keeping very well, if at all. And then finally, we had a great day. I think it was in February when it really snowed a lot. So so there are lane lines here. The concrete's here in the middle. And so can we figure out where we are relative to that concrete thing? So this was we're very fortunate to have that big snow. Under normal conditions, the two here are camera is the dark, and then the magnetometer based system with the electromagnetic material is the shaded one. This was for all the tests. So if it's clear weather and you have lane lines, cameras in this system work pretty well. So I'm not advocating here we would take out the camera based system because it worked pretty well. It's pretty well proven. Your Teslas have tons of cameras and they work well. But if you have, and these are just different types of motions. Again, this is in inches, by the way. So if in general, your air from ground truth is 2 inches in your lane, 2 out of 12 feet, 2 inches out of 144 inches. It's pretty good. I mean, you're not going to lose too much sleep over that. Now let's go to the snow covered. Oops, here. Wait a minute, what happened here? Oh, we skipped one here. Hold on. Oh yeah, this is snow cut. That's not snow covered. This is greater than 2 inches of snow. This one's greater than 2 inches of snow, and there's no camera here because you can't actually detect it at all. There's no lane lines to detect. So you can see even with 2 inches of snow, you're at 2.6 inches of overall air. And how did we know that? We put a yellow tape in the snow that we could see from our side view camera what the ground truth would be. This one here is, it does say normal here, but it's supposed to be for less than 1 inch of snow. That's not right. Actually, that's not right. There must be another one here. Oh, yeah, here it is, right here. Yeah, for the 1 inch of snow, it'd be the center one here. You can see that. Generally, the air on the magnetometer is pretty much the same, whether it's normal conditions or one less than 1 inch or 2 inches of snow. You can see where The camera system, of course, there's gonna be a huge amount of air with the camera system when you have 2 inches of snow, so I would just ignore that. If 1 inch of snow, it's still, 6 inches gets to be pretty big. But if you had 1 inch or 1.5 inches, it'd probably even get worse. Okay. Running out of time here, which is good. Hopefully what you've seen here, by the way, we're extending this to smart work zones now. We have a Pete Edge here. He's working on that with the new CCAT. It's obviously slightly different than this, but we also have, there's probably questions that'll come up, but there's obviously different materials I didn't show here that actually work better than steel fibers, particularly when you think about asphalt and the various different applications you would use. But the general concept's the same. You need to be able to somehow magnetize a material or bend the Earth's magnetic field somehow in a limited area so you can detect it. That's really the intellectual finding. And really, I think you can do this for a lot of lane miles. Pretty simple. There's many different ways to do it. So there's not just one way to do it. So I think that's a benefit. And I get back to the safety thing. If lane departures are really the way that are causing a lot of accidents, we really ought to focus on using the vehicle technology and it talking to the road to limit the amount of accidents that we're gonna, or at least try to prevent as many accidents as possible by warning people that they're leaving their lane. Whether it's rural, urban, whether someone's impaired, whether someone's in the texting, if you get warned, if you've driven an advanced driver assist car, it's very good. I mean, if you're not paying attention, it usually warns you you're gonna hit somebody and put some brakes on, and that's valuable. So thank you for your attention. I think that's it. Okay, back there in the back.
So hello, Professor, thank you for the great presentation. So I have a question I'm trying to understand at the same time as well. So this magnetic field increases the safety as long as it kind of overrides the data that was collected through cameras and sensors. And considering this for like autonomous feature, like don't you think having a physical material that can be altered externally creates a like all safety risk for like automation in general?
You think it creates more risk?
Yes, because like when you look at it, it needs to kind of override the data collected through cameras and sensors.
Sure.
And
Yeah, I mean, I understand your question, so I'll answer it this way. I think right now we're relying basically on the camera system to do the lane keeping and keep you in your lane. If that doesn't work, you have no other option. So if you want to imagine, in my view, if you want to imagine autonomous vehicles ever being working at high speeds, you have to have kind of a redundant system. And as far as I understand, I'm not a pilot, but as you fly a plane, you have kind of autopilot, you have a hydraulic system that you can fly the plane on with manually. You also have some mechanical system if the hydraulics failed. So even on a plane, there's not one way to fly. There's three ways. And I think it's the same analogy here. You've got to have multiple ways to navigate or maneuver the roadway, or you're going to be stuck with a system that only works under ideal conditions. So yeah, overriding it's probably the wrong word. I would say if you can't see it, you have to go to sensor number 2. Yes.
Thank you, Professor, for the nice presentation. Professor, I understand it is currently under patent, but I wanted to ask
Nothing on
you,
this. I mean, the general idea.
did you try using ferrites because they're used in transformers and they're
Well, met glass is used on transformers to shield them. So, yeah, that's that's the highest magnetic permeability material you can buy, and they're actually encased around transformers.
Thank you for the presentation. I think commend also Shindra, such a dedication to bolt something on his car and wait for snow. But I was curious if what was the thought of factoring in speed, if it affects data collection versus it's only a factor in input feedback to the correction of a vehicle? Because you brought up urban, rural, there are different speed conditions and how would it affect the system?
Yeah, that has to still be looked at more. If you're at lower speeds, I'm not worried about it, but yeah, if you're at 80 miles an hour. These aren't forward-looking sensors, they look down. The current system is a one-axis magnetometer, it looks downwards. Yeah, so, a nice thing about cameras, it looks forward. And you can project your trajectory of your car by looking forward. So we have some ideas on that we're currently, Apidage is buying sensors for that reason. But that is an issue that we have to fix. I wouldn't say it's not fixable. Yes.
Professor, like in the last couple of slides in the magnetometer where you compared the errors. So compared to the normal conditions for all other things, no at lesser than 1 inch had the lowest error. Why is that the case?
Well, one thing is the sensors are spaced 1 inch apart and Sachendra is driving the car. So he doesn't take the exact path every time. He's taking the path as best he can straight, but there is a human factor in that and where the magnetometers are relative to where they're trying to sense. So you can get an error just by not completely getting the sensors right over the top. So I would say, yeah, within an inch, you're pretty much the same.
I think, Professor, we are out of time, and obviously people can reach out to you if they need be. And thank you again for the great presentation.
Okay, thank you.